Alright, yo, what's up everyone? Welcome to Kinetics Part 5. Today we're going to do a bit of practice with the Kinetics unit. And today we're going to go over the 2021 local exam, and that's going to be from question 25 to, I think, question 31. So let's start with question 25. In the reaction, blah, 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 the rate of disappearance of F2 is 1 molar per second. What is the rate of appearance of ClF3? So remember, these relative rates are going to be stoichiometric. We see that the stoichiometric coefficient of the F2 is 3, and the stoichiometric coefficient of ClF3 is the 2 right here. So that means that 2 over 3 times the rate of disappearance of F2 is going to equal the rate of appearance of ClF3. And so we know the rate of disappearance of F2, that's going to be 1 molar per second. And so the rate of appearance of ClF3 is just going to be 0.67 moles per second. And our molarity per second. And so that's answer choice B, and that is correct. So again, the relative rate of disappearances and appearances are going to be stoichiometric. That's just what you need to remember. Let's move on. When the rate of when the rate of the reversible reaction A plus B to C is studied under a certain set of conditions, it is found that the rate of the forward reaction is Kf times the concentration of A. What can be concluded about the rate law of the reverse reaction under these conditions? Now, the trick answer here would just to say A, and that you would kind of get that if you just reverse the reaction, and it would just be C2A plus B. But you cannot do that since this reaction right here is not a elementary reaction, and so you need to find out a reaction mechanism that would produce this overall reaction. And so a particular reaction or a reaction mechanism that would work is if we took A and we put that in equilibrium with I is just some intermediate, and then we took I and then add that to B to produce C. And so since we're told that the rate of the forward reaction is this, then that's going to tell us that this top reaction, it would be the slow reaction. And obviously, if that's the slow reaction, the bottom one here would be the fast reaction. Okay, now that we have that, that's the stuff for the forward reaction. Let's reverse all these to get the reverse reaction. So let's reverse the first one. So I is now A, and that would still be the slow reaction. And then we have C2I plus B, and that would also be the fast reaction. So the reaction, the rate law here would be Kr times I. But remember, I is an intermediate, and we cannot have intermediates in our rate law. So what we can do is we can take the fast equilibrium step. Let me just erase the forward reaction so I have more space for this. So the K1 times C, that's the forward reaction, that's going to equal their reverse reaction, which is going to be I times B. So if we solve for I, it's going to be K1 over KB, or K negative 1, sorry, times C times B. And that's going to equal the concentration of I. So what we can do is now we can plug that in here. And all these K's are going to multiply and divide out. And we can just say that the final K is going to be Kr. And now if we just substitute for I, then that's just going to be C over B. And that's going to be the overall rate order, or the rate law for the reverse reaction. And so which one is, which answer choice is this? Well, that's going to be answer choice B. And that F should be an R, my bad. And the answer choice. And we are correct. So the important thing to notice is that we cannot just take the reaction that we're given and manipulate that, because it's not an elementary reaction. What we can do is we can make a reaction mechanism and then use that reaction mechanism to find the forward and the reverse rate laws. Let's move on to question 27. A substance A decomposes irreversibly to form B. A plot of the natural log of A as a function of time from the beginning of the reaction until A is 97% consumed is a straight line with a negative slope. What is the reaction order of A? So for this, you need to remember your integrated rate laws. And your integrated rate laws are going to tell you that the plot of the natural log of the concentration of A, if that's going to be linear and a downward slope, then you know that's going to be, let me just write this, you know that's going to be a first order reaction. Just as a review, let's review the other ones. If you had just the concentration of A over time, and that was a negative slope, that would be 0th order. And if you had 1 over the concentration of A over time, that would have a positive slope, and that would be 2nd order. But in this case, we have a negative slope and the natural log of A, so we are going to go with first order, and that is answer choice B, which is the right answer. Let's move on. Which statement about catalysis is correct? So let's go through all of them. A, if a catalyst increases the forward rate of a reaction by a factor of 2, it must increase the rate of a reverse reaction by a factor of 2. This makes sense because remember, catalysts do not change the position of equilibrium. It affects the forward rate and the reverse rate the same amount, so that the equilibrium just happens faster instead of at a different position. So A makes sense. Let's just keep it, and then let's look at the other ones. If a catalyst increases the rate of formation of a product by a factor of 2, it must increase the rate of formation of a mirror image of the product by a factor of 2. That just doesn't make sense. It's one of those like kind of dumb answers, or like your kind of guess answers. C, a catalyst must be in the same phase as the reactants and the products of the reaction. That's not true. That's only true for homogeneous catalysts, but you can also have heterogeneous catalysts. So C does not make sense. D, a catalyzed reaction must proceed by the same mechanism as the uncatalyzed reaction, but with a lower activation energy. This is not true. Catalyzed reactions can take a different reaction mechanism, and that could involve the changing of the elementary steps. So D does not make sense, and therefore the only one that makes sense is going to be answer choice A, which is in fact the right answer. Let's move on to the second to last one. The isotope 226 radium has half-life for radioactive decay of 1600 years. How long will it take the amount of 226 radium in a sample of 226 radium chloride to decrease by 25%? There is a trick answer here. You might think 25% implies half of a half-life, so that would be 800 years. But that's actually not true. It does not work like that. You need to use your integrated rate law. Remember, radioactive decay is going to follow first order integrated rate laws, and so the formula for our first order integrated rate law is the natural log of A at some time t is going to equal minus k times t plus the natural log of the initial concentration of A. So we can say that the initial concentration of our A was 100 molar, and so or molarity. And so at the end, when it decreases by 25%, our final concentration is going to be 75 molarity. And so we can plug that all in. So the natural log of 75 is going to equal minus k times t plus the natural log of the initial concentration, which is 100 molarity. Now we need to figure out one more thing, and that's going to be k. Since we're trying to solve for t, we need to figure out what k is. And remember, we can figure out k since we know our half-life. Remember, the half-life equation for a first order reaction is going to be the natural log of 2 over k. So if we know our half-life is 1600 years, we can do the little algebra here to figure out k. K is going to come out to about 4.33 times 10 to the negative fourth, and we can now plug that into our k over here. I'll save the work. Essentially, you just solve for t, and that gets you about 664-ish, and that's approximately 660 to the right sig figs, and so that's going to be answer choice A, which is the right answer. So again, when you have these types of questions, it's best to use the integrated rate laws, because then you know you are going to be getting the right answer always. The only times I would recommend not to use it is if you have something like decrease by 50% or 75%. These are at the exact half-life positions. But even then, generally just use the integrated rate law just to be sure, right? Let's move on to the last question, which tells us that the oxidation of the sulfide ion by blah 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 is proposed to take place by the following mechanism. What is the rate law predicted by this mechanism? Well, remember, we have to first we have to look at the slow step and write down the reaction rate for the slow step. So rate is going to equal Ks times SO3 2 minus times I2. But you see here that the I2 is actually an intermediate, so you need to figure out the rate law of this fast equilibrium to figure out how to substitute in for that I2. So uh, the forward reaction is going to be K1 times I3 minus, and then it's going to be equal to the reverse reaction, or the rate of the reverse reaction, which is going to be I2 times I minus. And so if you solve for I, you're going to get that I is going to, or I2 rather, you're going to get that it's going to be equal to K1 times I3 minus times K to the K minus 1 times I minus. Now, if you plug I2 into the slow step rate law, then you're just gonna get, it's gonna equal K times SO3 2 minus times I3 minus, and that's going to be over I minus, and that is going to be answer choice. Which one is it? Answer choice C, right here, and that is the right answer. So again, you have to figure out the slow step, use the use the fast equilibrium to set the forward and the reverse reactions equal to each other, and then solve for the intermediate that you need, and then you just plug it back in, do some simplifying, blah blah blah, and you'll get your overall rate law. Oh, so there's only it only goes up to question 30, this little section. So I guess it's not 31, it's 30. My fault. But that's all I have. I hope you learned something, and I hope you'll join me for our next unit, which is going to be equilibrium. Thank you for watching. I'll see you later.